You know, every single app on your phone, every website you visit, it's all built on a series of really fundamental choices. Choices about speed versus flexibility, efficiency versus power. Today, we're going to peel back the curtain on one of the most basic yet most important of those choices. Let's get into it. I mean, think about it for a second. It seems so simple, right? A grocery list, your contacts, a music playlist. But how does a computer actually hold on to that information in its memory so it can use it? The answer to that question is really the key to understanding so much about how software works, and maybe more importantly, how it breaks. And our story really starts with the most fundamental building block for any list you can imagine, this simple array. Okay, so what is an array? The best way to think about it is like an egg carton. Seriously. Each slot is the exact same size. They're all lined up right next to each other in a perfect row, and you know exactly where to find the third egg or the seventh egg, right? Well, in computer memory, an array is pretty much the same thing. It's just a block of these side-by-side slots, each one holding the same type of data. Now, this very simple, very rigid structure is exactly what gives the array its superpower. Because all those egg slots are in a predictable line, the computer doesn't have to go searching for an item. It can do a tiny bit of math and poof, jump directly to any element's location, instantly. In computer science, we have a name for this. We call it O of 1, or constant time performance. That O just stands for order of, and the 1 basically means it's a single constant step. Think about that. It takes the exact same amount of time to grab the fifth item in a list as it does to grab the 5 millionth. It is blazingly fast. But you knew there was a catch, right? Like any good story, there's always a conflict. And that incredible speed, well, it comes at a price. There are always trade-offs. And here it is. This is the array's Achilles heel. When you first create an array, you have to decide exactly how big it's going to be, right up front. If you have an egg carton made for 12 eggs, you can't just magically fit its 13th egg into it. Its size is set in stone. So what happens if you need to add an item somewhere in the middle or at the beginning of your list? Well, it's a disaster. To insert just one new item, you have to scoot over every single element that comes after it, one by one. Imagine you have 1,000,000 items. That means you're doing 1,000,000 of these little scoot over operations. It is incredibly slow. So this table is basically the array's performance report card. Looking up an item or tacking one on to the very end, that's O of 1, super fast. But inserting, deleting, or even just searching for something, that's O of n. The n here just stands for the number of items in the list. It means the time it takes grows directly with how big your list is. That's that painful scooting over process we just saw in action. Okay, so if these simple static arrays are so rigid, how does your phone's contact list just, grow whenever you add a new friend? Well, programmers came up with a really clever solution that actually builds on top of the simple array. And that's where we meet the dynamic array. The core difference here is a classic trade-off. A static array is super simple and efficient with memory, but the dynamic array gives you the flexibility to grow because it pre-allocates extra memory just in case. But that growth isn't really magic. When a dynamic array runs out of its pre-allocated space, it has to perform a pretty costly operation behind the scenes. It creates a brand new, bigger array somewhere else in memory, and then it has to painstakingly copy every single element from the old one over to the new one, and then it throws the old one away. This is why sometimes adding just one more photo to an album can cause a brief but totally noticeable pause. Now, all these arrays, whether they're static or dynamic, they need a place to live in the computer's memory. But that memory, it's not an infinite resource, and the way programs manage that finite space can lead to some, well, let's just say interesting problems. And that brings us to one of the most famous errors in all of computing. To understand this error, we need to think about a different kind of structure. And this analogy is just brilliant. A pile of dishes, right? In programming, we call this a stack. You always add a new dish to the top, and you always take the top dish off. Last one on the pile is the first one off. So your computer uses this pile of dishes idea for something called the call stack. It's basically how it keeps track of what it's doing at any given moment. When one piece of code, we call it a function, needs to run another function, it's like putting a new dish on the stack to remember where it left off. So let's say your program starts running function A. Boom, one dish gets placed on the stack. Then, in the middle of its work, function A needs function B to do something for it. Okay, so a second dish is placed right on top of the first one. The stack gets taller. Now just imagine this happening over and over and over again.
But what happens when you run out of room in the cupboard? What happens when that pile of dishes gets so high that it hits the shelf above it?
This, a stack overflow. The program tried to add one more dish, one more function call, onto a stack that was already completely full. There's just no more memory allocated for it. And with nowhere to go, the entire thing comes crashing down. The program fails. So, from simple egg cartons to overflowing piles of dishes, what's the big picture here? Why does any of this actually matter to you or me? Well, it all comes down to this eternal trade-off that software developers face every single day. Do you go with the raw, predictable speed of a simple array, or do you pay a little price in performance and memory to get the power and flexibility of a dynamic one? So if we put it all together, here's what you should really take away. Arrays are that fast, simple workhorse for storing lists, but they're rigid. Dynamic arrays give us the flexibility we need, but it comes at the cost of memory and those occasional slowdowns. And all of this is happening inside the finite limits of your computer's memory, where pushing those limits can cause catastrophic failures like a stack overflow. These fundamental choices, they're at the very heart of how every single piece of software you use actually performs. The next time your favorite app pauses for just a split second, you might have a better idea of the invisible dance that's happening just behind the screen. And it makes you wonder, doesn't it? What other fundamental trade-offs are shaping the technology we use every single day?